As I said, thank you for giving me the opportunity to talk a little bit about the SLS upgrade and showcase some of the highlights which we hope to exploit to great effect with the upgraded machine. Yeah, so I will be talking in general about synchrotrons. I hope this isn't too obvious for everybody. As a consequence, how DLSRs, which are the 4th generation, differ from the 3rd generation facilities, which started in about 1994 with the ESRF going online in Grenoble. I will then talk a little bit about the numbers and statistics and parameters of SLS2 compared to SLS, the original, and then give some science drivers for SLS2 and where the directions we hope to go in. Okay, so I'm sure some of you will recognize this image here, but just for those who do not, this is a schematic of a synchrotron, and this consists of an electron gun and a linear accelerator, which accelerates these electrons into a booster ring, which then accelerates the electrons. It's a true synchrotron up to the so-called storage ring energy, which is measured in giga-electron volts. And then the electrons are further injected into the so-called storage ring, where they are kept on a closed path by the bending magnets. Now, the bending magnets seem to be a somewhat prosaic aspect of modern synchrotrons, but in fact, they are essentially the core aspect of what makes DLSRs different from the 3rd generation facility. Now, in between these bending magnets, we have straight sections, which include insertion devices, and most facilities like to use the insertion devices to get the highest brilliance and best quality radiation, X-radiation. And that radiation goes into a beamline where the experiment is carried out. Okay, so I think everybody's familiar with this. If you think about who uses synchrotrons, it is really one of the most multidisciplinary tools available to the natural sciences. And this is just a selection of some of the areas of research which can benefit from the use of synchrotrons. I'm sure there are others which are not mentioned here, which I've not included. But as you can see, it's no longer the domain of physicists and chemists, but actually it is the biologists, if anyone, who tend to dominate the use of synchrotrons nowadays. Okay, so what makes a synchrotron interesting? Well, first of all, the intensity of the radiation is extremely high. The radiation is very parallel. One uses just a narrow bandwidth, and the source size of that radiation is very small. Now, one can bring all of these together. First, flux, well, spectral flux, which is defined as the photons per second per 0.1% bandwidth, and the emittance, which is simply the source size in units of square millimeters, and divergence in units of square milliradians. If one brings this emittance underneath, then the full characterization of a figure of merit for a synchrotron is given by the flux divided by the emittance, measured in photons per second per 0.1% bandwidth per milliradian squared per square millimeter. Okay, so that's a parameter or a figure of merit which you should keep in mind. And if one looks at the brilliance of X-ray sources historically, one sees that there was very little change between the original Coolidge tube and maybe an order of magnitude improvement half a century later through the introduction of a rotating anode. It was really when X radiation was used as a parasitic, in a parasitic mode at high energy nuclear facilities, such as at DAISY, that bending magnet radiation could increase the brilliance by something like 4 or 5 orders of magnitude. And then the introduction of insertion devices in the 3rd generation facilities really took things to the region of around 10 to the 20 and 10 to the 21 photons per second millimeter squared, 0.1% bandwidth. Now, in 2009, I believe it was, the first light came from the LCLS in Menlo Park, and XR radiation took things up by another 9 to 10 orders of magnitude. And this actually meant that the sort of experiments which are done there are fundamentally different from the experiments which are done at synchrotrons, primarily due to the fact that oftentimes the samples which are looked at are destroyed by the X-felt pulse. But there is a gap in between which is really now being filled up by DLSRs. They have up to 2 orders of magnitude higher brilliance than is presently possible on 3rd generation facilities, and it is this which I'd like to talk about in a little more detail today, specifically with regards to the SLS upgrade. Just as a interesting point, one often hears about Moore's law and the exponential increase in computing power as a function of time. And if one actually looks at the gradient on this semi-logarithmic graph here of the progress of X-ray sources, one sees that it outpaces that of Moore's law by some substantial margin. Okay, so what is a DLSR? What defines the 4th generation facility? Well, the 3rd generation facility was essentially defined by an improvement in the flux, by the introduction of insertion devices. It also, to an extent, had something to do with the natural narrow bandwidth associated with undulators, but it was really this increase in flux which defined these 3rd generation facilities. Now, in these 4th generation facilities, what has produced this next 2 orders of magnitude improvement in brilliance has been a reduction in the source size and superior collimation of the emitted X radiation. In order to fully understand this, we need to first, and I'll just be a little bit didactic here for the next 3 or 4 slides. One needs to understand this total emittance. We have a certain source size, which we call sigma, and sigma prime is the divergence. So we're just talking about in one plane here, in say the horizontal plane. Now there is a certain emittance or source size multiplied by source divergence associated with the electron beam. But there is also a fundamental photon emittance, or so-called single electron emittance, associated purely with the emission of photons. And this is really a fundamental diffraction effect and cannot be played with. If you look at the photon source size, it's given by this equation here for an undulator of length L, and the divergence is given by this expression here. And if we multiply these two together, it emerges that the photon emittance is only defined as being dependent on the wavelength of the radiation that you're using. Now, the total emittance is a convolution of the electron emittance, which I'm showing in blue, and the photon emittance, which I show in this gold color. So they add orthogonally, and this is why I show this little Pythagoras triangle here. But the total emittance, which I show in green, is a convolution of the two. Now, the electron emittance, we can vary how the emittance is divided up between the source size and the divergence via the so-called beta function, which can be varied along the storage ring by the use of electron optics. So in the case of the electrons, you can play with how the emittance expresses itself. Am I a large beam which is very parallel, or am I a small beam which is much more divergent? If we consider, for example, the photon emittance, which, as I've said, is a fixed parameter, and for a given undulator length, the ratio of sigma prime to sigma, in other words, the aspect ratio of this ellipse, is fixed. But, as I said, the electron emittance isn't. But if we make the electron emittance have the same aspect ratio as that of the photon emittance, then we have a well-matched facility, or well-matched source. And if we look at the opposite case, for example, if it were to be like this, then we can clearly see that the total emittance is much larger than in the left-hand case. Okay, so what we really need to do here is consider what the beta function is at a particular point to match best the radiation in which we want to produce. Now, at third generation facilities, without going into all the numbers shown here, we see that even for soft X radiation at around 100 electron volts, that the photon emittance is pretty small compared to the electron emittance. And at higher photon energies, lower wavelengths, it becomes even smaller and smaller. Hence, the impact of the matching of the photon and electron emittance doesn't really have very much of a influence on the final product. The reason being is that the electron emittance dominates in all the cases. This is for an electron emittance, for example, of around 5 nanometer radians, which is typical for a third generation facility. Now, if we look at the same situation now at a fourth generation DLSR, a hypothetical situation where we have only 100 picometer radians, so in other words, something which is 50 times lower electron emittance than we had before, then we see that, for example, in the case of the soft X-rays at around 120 electron volts, that the photon emittance now dominates quite substantially, and that around 1,000 electron volts, they're of a very similar size, and only if one gets up to hard X-rays does the electron emittance start to dominate again. So in other words, for these fourth generation facilities, matching the electron emittance to the photon emittance is important, actually for over the entire photon range of interest. Now, how do we actually get this? How do we get a factor of 50 or 100 times improvement in the electron emittance? Without going into the machine physics behind this, I will simply state that this an electron emittance in the orbital plane of a so-called multi-bend achromat. Let me step back here for a moment. In a third generation facility, typically a bending magnet arc section would have 2 bending magnets in a so-called double bend achromat. A couple of facilities had 3 bends in the triple bend achromat, but that I think only confuses things. What one should just keep in mind is that in most third generation facilities, DBAs, double bend achromats, were used. The whole concept behind DLSRs is to break up the same arc length into much smaller segments of bending magnets where there are multiple bending magnets. In this case, I have shown just 6, but 7 is a more typical number. And as a result, the angle subtended by any one of these bending magnets is smaller. Now, it emerges that the emittance of the electron emittance of a multi-band achromat is given by m+1, where m is the number of dipoles in the arc, divided by 3m-1, multiplied by a certain constant, called the double bend achromat constant, and then these two parameters, gamma squared, which is gamma is proportional to the storage ring energy, and most importantly, it's dependent on the cube of the angle subtended by a single dipole. Just for a sanity check, if we put m is equal to 2, then we have 3 divided by 1, and then all of these terms cancel out, and we just get to the emittance for a double bend achromat. So, for example, if we were to replace a double bend achromat with a 7 bend achromat, we would end up with in theory, an improvement of nearly 100, all other things being equal. Okay. Oh, sorry. For some reason, it's not. It's frozen. Can people hear me?
Yeah, we can hear you, but
oh, sorry, for some reason my yeah. Now it started working again. Sorry about this. Let me share the screen again. Okay, I'm back. Now, if we look at the upgrade programs of various facilities here, shown in blue, compared to the present third generation facilities, we see this between factor of 10 and factor of 30 or 40 improvement in the emittance. And we can see wait a moment, the SLS goes from here to SLS to here. What I show on the right-hand side is essentially the same plot, but I've multiplied by the cube of the circumference, because this is sort of proportional to the subtended angle for any one beamline. For any one achromat. Okay, now, but there are knock-on effects which we might not at first recognize due to the fact we're now using a DLSR. If we look at the third generation, the electron beam has got a width of maybe 100 microns or thereabouts, and an amplitude of maybe only 1 micron. So this, the way that the electron beam undulates through the insertion device. This means that an observer can see a substantial amount of off-axis radiation due to the width of this river of electrons. In the case of the fourth generation, the width of the stream, as it were, is maybe 10 or 30 times smaller, or that sort of order of magnitude, and the amount of off-axis radiation that one sees is substantially reduced. Now, this off-axis radiation produces these large lobes, which you can see in this plot of an undulator spectrum at a theoretical third-generation facility, which has an electron emittance of 5.5 nanometer radians. Now, I'm just going to run this animation here to go from 5,500 picometer radians, 5.5 nanometer radians, down to 140 picometer radians. And one sees that as one moves to this lower electron emittance, that the side lobes become smaller and smaller and smaller, and these undulator spectra become increasingly clean. And this becomes very interesting when one wants to use the entirety of an undulator harmonic for experiments where one wants to get more flux and one doesn't necessarily want to use a monochromator in order to make your radiation bandwidth even narrower. Lastly, I'd just like to quickly mention something about coherence as we sort of define it as a synchrotron. So we may have a broad band and large source, but we can, of course, make a secondary source by inserting a pinhole, and this will give a good degree of so-called transverse coherence, and then we can filter this using some sort of monochromator, for example, in order to obtain a good longitudinal or temporal coherence. And in fact, if we look at the increase in the coherent fraction between a third generation facility and a fourth generation facility, we see that this will increase enormously due to the reduced source size, in other words, our slit, and the reduced source divergence, in other words, the reduced emittance. And if we now run this animation, leaving the third generation behind, we see that as our emittance goes down into the hundreds of picometer regime, we get a huge increase in the coherent fraction. So we see that there's only a factor of about 1.5 increase down at around 10 electron volts, but up at 100 kilo electron volts, we have a factor of around 100 improvement in the coherent fraction. For the hard X-ray regime, the increase in brilliance corresponds 1-to-1 with the increase in the coherent fraction. Now you might say, okay, well, look, the coherent fraction in the soft X-ray regime is anyway high, so why don't we just do our experiments there? For many instances, this is not practical. The reason being that we need the hard X-rays, the high transmission, and the small wavelength in order to do nanoscale imaging techniques. So really, this huge improvement in coherent fraction, which we see here in the hard X-ray regime, above anything above a couple of kilo electron volts, is of huge interest to the imaging community, particularly for those people who use the coherent part of the X radiation. So just to summarize this, if we assume that our improvement in horizontal electron emittance is something that we want, then this results in a tighter focus beam, a more parallel beam, and a higher coherent fraction. But like I've just said, there are knock-on effects, such as new source technologies and the possibility of novel X-ray optics, which combined can result in increased flux and higher photon energies being accessed for a given beam, for a given facility, for given facility parameters. The tight focus is very interesting if one wants, for example, to work at a large working distance for complex sample environments. So you might not want to take advantage of getting an even smaller spot size, but instead just have the same spot size, but now using optics, which have not got such a short focal length, meaning that you can start to have much more sophisticated environmental chambers for many different sorts of experiments, typically things like in catalysis. Also, very tight focuses means that one can start to look at sample heterogeneity and domains on the micron and even submicron level. A parallel beam, of course, is a bit of a prerequisite for good quality X-ray diffraction experiments, whereas the coherent fraction is important for XPCS, X-ray photocorrelation spectroscopy. The increased flux and higher photon energy is important for time-resolved XRD, surface X-ray diffraction, X-ray reflectivity, Zernicke microscopy and zoom microscopy, and fast X-ray tomography. This combined with the high coherent fraction is very important, extremely important for one of the most important emerging techniques is ptychography, which is a variant of lensless imaging, and phase contrast X-ray tomography. But there's not just this, the high increased flux and combined with looking at real samples, operando samples, for example, make the techniques of nano-ARPIS and nano-RICS extremely important, also in the soft X-ray regime when looking at device structures. And then lastly, the large working distance, like I said, is very interesting for techniques such as ambient pressure photoelectron spectroscopy, high pressure X-ray diffraction, and different forms of X-ray absorption spectroscopy, such as in catalysis. Also, heterogeneity and tight focus means that one can do micron scanning X-ray diffraction. And then finally, the tight focus and parallel beam, if you want both. These are very important for scanning imaging spectroscopies and for protein crystallography, and a variant of that, which I will briefly mention later, serial synchrotron spectroscopy. Okay, and I seem to have frozen again. Ah, no. Ah, excellent. Okay, good. So a little bit of a history about the SLS. We got our first light in April 2001. And since the Digital User Office has been operational in 2006, we've had over 55,000 user visits and over 700,000 hours of user beam time. There are in excess of 7,500 PDB structures since 2002, and many more above that through industry, which are obviously not made public, of protein ligand complexes. Our impact factor journals, our cumulative publication count can be seen here on the right. And excuse me, now it's going by itself. And these are divided up into publications below an impact factor of 7.4, an impact factor of above 25, and those in between. So what differentiates the SLS from the SLS 2.0? First of all, we've gone actually up in storage ring energy. If one remembers some of the background information I gave about DLSRs, it's actually an idea not to go too high in storage ring energy because the emittance scales with the square of that storage ring energy. However, it also means that one can access higher photon energies for a given undulator facility or undulator source. So this was deemed something which we would like to do. The new ring has a different footprint, and one actually sees that it's about 2 meters longer. This will mean that we actually have to tear down the entire storage ring and rebuild it from scratch. We will have the same current, and we'll be going from this triple bend achromat system, which we've been using since 2001, to a 7-bend achromat system with so-called reverse bends inside. I don't want to go into details of this in today's lecture, but if people have questions about that, I'm more than happy to answer those. And all other things being equal, we should have an improvement by about a factor of 30 or 35 from what we presently are able to get at SLS. Importantly, we're also adding new beamlines. So we have 12 straights. One of those, of course, needs to be used for the injection, but we were not using 2 of the other ones up until now. And those 2 straights will be used in the future. So we have a total of 11 straights used for insertion device beamlines. And this is actually what the portfolio will look like. Now, for those of you who are not familiar with the SLS, these names will not mean a huge amount to you. So here I will only say that we have new beamlines Dubai, which is an industry beamline for chemical kinetics and catalysis, and a brand new insertion device tomography beamline, which will be the sister beamline of the present Tomcat beamline at the SLS. But over and above that, there are some beamlines which are moving to new locations and will be built essentially completely fresh. And The Quest beamline, for example, is a conglomeration of the old Pearl beamline and the old Cis beamline, so extending the electron spectroscopy and the chemical XPS capabilities into one larger beamline. Please feel free to look at the beamline CDR. It's a large document, about 300 pages, at this link here. What is perhaps a little more useful is this figure here, in which the techniques which are generally used at these different beamlines and their photon energy range are given. I don't need to go through that one by one. I leave it to you to look at those numbers at your leisure. Just to highlight the beamlines which have a bold border, means that they are either a bending magnet if they're blue, or a super bend if they are green. Yeah. And this is essentially an overview of the brilliance of the different sources which we will be using at the SLS2 facility. Okay, so we have this substantial improvement around factor of 35, but that's really just the emittance. But the brilliance, of course, is not just a question of the emittance, but also a question of flux, as was exploited in the third generation facilities. And in fact, we will be looking into that, be exploiting that as well. So we'll be trying to improve things in the numerator and the denominator, both. And if we actually look at the factor improvements in the brilliance, the flux, the coherent fraction and coherent flux, we see, for example, improvements in brilliance up to a factor of around 1,000 in the hard X-ray regime. And this is being made possible not just by the improvement in the emittance, but also more intense radiation being produced by novel developments in short period, high K, cryogenically cooled permanent magnet undulators, and also in a completely new research direction, these high temperature superconducting undulators with periodicities of only 10 millimeters. We see that we get a factor of 100 times improvement in flux at 50 keV compared to the U14, which is presently our shortest period undulator at SLS. So these two things combined will hopefully produce brilliances up to a factor of about 1,000 compared to what we can get today. A little bit about the timeline for the SLS2 upgrade. This is the date today. We define the storage ring in the middle of 2020. We define the beamlines and their positions towards the end of that year. And we actually got the funding only guaranteed at the beginning of 2021. We want to be able to really say we're going ahead, that there are not substantial delays towards September, about a year from now, in 2022. So this is basically our go, no go for what the timeline is further down. And we will start the dark time at the beginning of October in 2023. And this will continue for 15 months of the tunnel wall being open, followed by 3 or 4 months of commissioning, and after which nominal beam will be available. And then about 3 months later, user operation will start. Now, unfortunately, we will not be able to do all of the beamlines in one go. So we will have a second 3-month shutdown in which the mainly soft X-ray facilities are installed, and then 3 months of commissioning, and we will restart user operation in the summer of 2026. All right, I'd like to finish my talk now by showcasing some of the science opportunities which we hope SLS will be able to offer. First, maybe a little bit about COVID-19 research. We always kept the protein crystallography beamlines open and some of the other ones as well. We had special COVID calls for beam time, and these are just some of the examples of the structures which came out. If you want to look into detail about this, there is a summary at this link shown here. We also looked, for example, using Tomcat, the tomography beamline, at a rat lung at a resolution of 2.75 microns and a total number of voxels in the range of 600 gigavoxels. This can be found at this link here. We also looked at fragment screening for COVID experiments, and of course this is to a large extent automated. So people would send in their different, many hundreds of different crystals, and these would be looked at successively at our protein crystallography beamlines. So talking about protein crystallography, we have three beamlines. We have two which are insertion devices. EXO-6SA is our flagship beamline where we do a lot of novel research and different high-risk experiments. The other insertion device beamline, X10SA, was originally made to be more or less a clone of 6, but this is purely for industry. And this will be completely funded, the upgrade for that will be completely funded by industry, with the exception of the undulator, which we will pay for. And then we had a superbend beamline. This is EXO-6DA. And we see how the improvements are in reduction in beam size and increase in flux on the sample at 12.4 kiloelectron volts. And the way that the protein crystallography team have been selling themselves is under the moniker of 1 to the 4th. I know 1 to the 4th is still 1, but the idea here is that they will be able to do experiments, standard experiments at a full data set within 1 second. They hope also to be able to look at crystals which are of the size of around 1 micron and do time resolved studies with a resolution down to about 1 microsecond and look at single wavelength anomalous dispersion experiments with just 1% variations between the Friedel pairs due to native Friedel breaking, particularly obviously of the sulfur atoms which are within the molecule, within the proteins. So regarding the fragment screening, crystal growth technology has reached something of a stasis, but the industry would therefore like to say, well, you know, we're not really getting very much further with our crystal growth properties and our skills. So what we'd like to do is actually start to use some of the poorer crystals. So it exploits a large volume of small volume material. Now, in the newer synchrotrons, there are novel ways of handling these kind of very tiny crystal samples. For example, as a jet or a toothpaste, which was originally developed for the XFEL, or a fixed membrane, or indeed acoustic levitation. One sees a nice little video here of a small sample just being spat into this acoustic levitator. And of course, everything nowadays is done to a large extent through automatization. So the precise location and orientation of small fragments on a large biological target is important for fragment screening. So we really need high resolution of about an angstrom or better, and a fast throughput. Presently, we can get through about 30 fragment samples per hour, and it takes about 10 minutes to get a structural solution. So the bottleneck is really the use of off-site supercomputers to accelerate this a little bit. Now, the crystals can be very small, and the reason for this is a lot of the crystals of interest, membrane proteins and GPCRs, are hydrophobic and therefore do not easily form crystals. There are ways to try and trick them into this using different sorts of media. But importantly, they represent in reality about a third of all proteins and 2/3 of all drug targets. So we really want to be able to look at these hard to crystallize protein types. So this will require both a small and parallel beams and high intensities. And this is what makes DLSR so interesting. Note also that automation means that from 2025 onwards, we predict that we will be generating between 10 and 100 terabytes of data per day. So IT in and of itself is a subject which has to be taken extremely seriously in this new generation of synchrotron facilities. Oops. Now, serial synchrotron crystallography is, for some reason, not running. Exactly. This is a technique one takes a jet or a toothpaste and one hits these tiny crystallites here, and they all come in at a random direction. The consequence of this is that we don't have a nicely formed regular pattern of diffraction pattern coming in a predictable manner, but in fact they all come in random directions, and one has to record huge volumes of data in order to fill the eval sphere with the fill reciprocal space with this data. But fortunately, because we have very high brilliance and flux, this is something which hopefully the next generation of synchrotrons will really excel at. And finally, something a little bit about low energy native SAD. This is basically the anomalous signal between Friedel pairs between -200% and +200%. And one sees that we're exactly at the edge, and we're coming up to it here. If we look at the spot on the right, we get very large anomalous patterns indeed. But as soon as one starts to move away from that, this goes down to very small amounts. But at the PX3 beamline, we will be running in this sort of regime where these anomalous breaking of the Friedel's law is only in a few percent range, but we do hope to be able to get direct structural information through this SAD technique, native SAD technique. Okay. Now, imaging at SLS 2.0, the CSAX beamline has really been a pioneer in X-ray tychographic imaging. I show here an example of tychographic so-called laminography, where the sample has got a leaf-like nature. In other words, in 2 dimensions it's large, and in the 3rd dimension it's small. So this is actually a silicon chip. But here one really gets down to 7 nanometer resolution in 3D. And this was published in 2019 by Holler et al. In Nature Electronics. We hope to be able to do this sort of experiment of at around 100 times faster speeds once the DLSR is online. Should be noted that we will also try and take advantage of the coherent flux increase even in the soft X-ray regime, and already the SIN beamline has been looking at magnetic gigahertz dynamics in cobalt permalloy structures revealed by XMCD, so X-ray magnetic circular dichroism tychography at the SIN beamline at the cobalt L edge. In full field tomography, we've done amazing experiments with very, very large data sets of large samples down to micron resolution, as given, for example, in this paper here by A. Mietenen et al., and fast tomography. In the past, we always showed our fly, the fly's muscles, but when one actually, this may not look quite as exciting as the fly, but here we're recording 1,000 tomograms per second. This is not 1,000 images per second, this is 1,000 tomograms. So we're talking around 180,000 images of that order of magnitude per second. This can only be done using phase contrast tomography. And of course, this increase in flux, and even higher still for the high temperature superconducting undulator at around 50 kiloelectron volts, will be a game changer for this kind of technique. Yes, tychographic nanotomography. This is a lensless imaging technique which relies on the speckle pattern produced by the coherent part of the beam. So obviously this is improved by a factor of around 35. In other words, the same as the improvement in the emittance. And we really hope, using just the machine improvements alone, to really bring tychography into a new regime. But like I said, we also hope to improve the flux coming out of some of these short period undulators also by approximately a factor of 10. Plus some tricks with optics may mean that we can really improve things by around a factor of 1,000. I've just shown this already, just briefly, but this is the longer video of the Intel chip, which was looked at using laminography. In other words, this device where the silicon chip is tilted at an angle so that the X-ray beam never sees the edge on sample, which would have an unacceptably high absorption. This is a lovely piece of work also done by CSACS, in which a comparison was made between a healthy and a Parkinson's diseased brain tissue, and how, for example, in particular, that there is a swelling along the axons given by this purpley blue color here, and neuromelanin containing organelles are more obvious or more common in the Parkinson's diseased patient. We've also been able to look at magnetic tychography in the hard X-ray regime, and like I also said before, this is now being done at the SIM beam line at around the L edges of the magnetic elements around cobalt, iron, and nickel. This is a beautiful video recorded through Tomcat of this full field tomography of a mouse brain, which was made possible through a so-called stitching algorithm, where one takes smaller volumes and then stitches them together in a flexible manner. And like I say, this is can be this research is reported in this paper here. So well, this is just a summary of the anticipated gains for a certain selected beamlines. Again, I will not go over each individual numbers, but this is something which you can look at your leisure afterwards. So in conclusion, I've given a little bit of a didactic overview as to what a synchrotron is, its figure of merit, in other words, the brilliance, and how the brilliance improves by the use of multi-bend achromats. I also tried to show that the improvement in the horizontal emittance has a number of knock-on effects, which then has a very large impact on almost all of the techniques which we use at the Swiss light source. I also showed the portfolio of the SLS, and then gave some highlights of some of the scientific directions which we hope to go into. I should say that I only mentioned a few of these. I left out, for example, some very important science which we're doing using RICS and soft X-ray ARPIS, but given the limited length of time, I decided to remain mainly on protein crystallography and imaging. So with that, I'm more than happy to answer any of your questions. I would just like to say also that some of the animations which I showed here are available on this website here called synchrotronmovies.com. They tend to be mainly of a didactic nature, but could be of interest to those of you who do any teaching or indeed give a lot of talks on synchrotron radiation. So thank you again for your attention.
Thank you, Philip. Thanks a lot. That was a very informative and extremely nice talk. And now I ask the audience if they want to ask questions, they can unmute themselves. Yes, Stephen.
Hey, yeah, thanks, Phil. Really nice talk. It's going to be pretty exciting having this upgrade. A few questions come to mind. I guess one is, I guess the time schedule was to go dark in about a year's time. Is that correct?
No, in 2 years' time.
2 years' time. Sorry. Okay. So that gives us a bit more time, but the question is still valid, I guess. How are you going to handle then the next 2 years of users? Is it just going to be a normal call, or is it? I mean, people are going to be trying to get in there.
Exactly. So yes, we will have normal calls all up to the end of September 2023, and people have to realize that thereafter we will be out for 18 months for the hard X-rays and even longer for the soft X-rays. And we're trying as much as possible to have a quid pro quo with some of the other facilities, particularly in Europe. I'm thinking mainly about Diamond, ESRF, maybe Max4 as well, where there are reciprocal needs.
Okay.
We are also, of course, telling people not to now start to apply for PhD positions and then letting some poor guy have 2 months of beam time and then he's out for 1.5 or 2 years. So we're trying to avoid that as well. That's a bit of a no-brainer.
Yeah, that's an important thing to say. That's very good. And then another question. Then, you now have you're splitting Tomcat into two, or you're creating a new version and keeping the old one. So, what would be the strategy then for applying now? Would one apply for tomography, and then the review panel or beamline scientist would allocate the beamline, or will there be a certain focus for one beamline versus the other, so we can target one or the other?
Right. So certain. So yeah, I haven't. Unfortunately, I don't have it exactly on the top of my head now, but I know that the just regarding sample size, if you've got a sample which is around 1 millimeter or smaller, you'd be wanting to go to the iTomcat beamline. If you have a sample which is substantially larger than that, up to 50 millimeters or so, you would want to go to the S-Tomcat, the superbend beamline. But over and above that, you know, do you want to do fast tomography? Do you want to do phase contrast tomography? Some significant research is being done into trying to extract more information from the fringes produced in coherent tomography past the single fringe, which classically people use just to get your line drawing edge contrast. If we really want to go to these very, very fast XTM techniques, it may be necessary to have the undulator radiation in order to get sufficient amount of coherent signal out of that. I'm not an expert in that area, so don't quote me.
Okay, but I'm just thinking of some users who maybe less familiar with the beamlines, and so they're not sure which one to apply for. How will you handle that? Because it's often a challenge. You're already between different facilities. It's a challenge to decide which one within a facility. Then you want to do tomography. Okay, there's a scale range. You're going to guidelines, or will it be a little bit of flexibility on your part to say, actually, we'll pass this over to the other review panel?
I actually don't know the answer to that question. I would have to speak with Marco about that, just to, if they see if they clearly see this is a good project, but they've applied to the wrong station, then I could imagine that they would just push it over to the other one. I don't think there will be separate calls for S-Tomcat and I-Tomcat. I think it'll just be calls for tomography at Tomcat 2.0. So yeah, the umbrella concept of the new Tomcat facility is Tomcat 2.0, which includes now 2 sources.
Okay, that's a very good way of organizing it. So yeah, it keeps it easier for the external people to understand. Yeah, and then the same group working out. It's brilliant because it's very successful beamline. So good, thanks.